Okay. So today we've covered pretty much like 90% of like the theory and conceptual stuff you need to know. Um, Today we'll be talking a lot about implementation. Like how do you actually code this? How would you train something in practice? So just to briefly start with a review. Um, so last time we covered two parts of training, right? You have a forward pass over here and a backwards pass. So the idea is for every data point in your data set, you first do a forward pass, which means you get the prediction, right, of how your model does on that one data point. And then you calculate the loss, which tells you how bad your prediction did, right? And so then we then take this loss and then use it to do something called a back propagation. And let's just be a little more specific now. So down here is our neural network. You can see we have one weight, one bias, and then an activation. So these three components form a single neuron. We then have a one weight and then a second bias. And these two together form the second neuron, but there's no activation here. So what we do is we send this input of 2 through the entire neural network, and we get an output of 1.8. Well, the actual output was 3. So that was pretty bad. Now, how bad? Well, the loss tells us how bad we did. Remember, a loss of 0 means we did like perfect. It will never have a negative loss. Okay. So again, forward pass is for every single data point. Here, I just have one. You calculate what the model thinks the output should be, and then you get the corresponding loss. Okay. Back propagation tells us how do we use that loss to fix our model. And I not to get into too much detail, but I've underlined the parameters, so our weights and biases. And these are the things that at first we randomly initialize because we don't know what they should be. But through back propagation, we slowly, iteratively push them in the right direction. So we get the weights and biases that make our models work. So you can see here, for example, originally I randomly initialized the value of like 0.8 for weight 2. And then after back propagation, it bumps that up to 0.82. The idea is I keep incrementally changing these weights and biases to get the correct outputs. Okay, so we do this training process, forward and back propagation, with our training data set. We then want to test our model with a separate set of data called our test data set. And so you might remember from last lecture, if our model does really, really well on the training data set, so the loss just decreases, right? Versus we give it data it's never seen before. So our test data set, if it is well on trained but bad on test, that means you've overfitted the model. If it is bad on both, so the loss never decreases during training, you've underfitted the model. When I say fit, I mean how well did the model learn the patterns in the data set? And so some ways to assess how good our model did are just accuracy, precision, recall. For our intents and purposes, we'll primarily be focused on accuracy. But these are some other ways to assess how good your model did. Okay. So we'll be talking about the iris dataset for our problem we're going to try to solve today. So the iris dataset consists of 150 samples of data for flowers, specifically the iris flower. So we have 3 features, and remember the features are the data that's being fed to our model, right? So we have the length of the sepal, the width of the sepal, the length of each petal, the length of the petal, the width of the petal, right? And so again, we want to create a model that takes these 4 features and is able to correctly output the species of flower, right? So does anyone remember? So we're trying to predict 3 discrete classes: Setosa, Varicolour, Virginica, the 3 different types of irises. Does anyone remember if this is a regression problem or a classification problem? Classification, yeah. I said it with the word class. Yeah, great, good job. And again, given the flower data, so the 4 features predict the corresponding flower. Okay, so moving on to how we're going to go about coding this. So kind of the go-to language for machine learning is usually Python, because it has some really, really nice libraries for us to use. The 2 big ones are TensorFlow and PyTorch. Most machine learning faculty here use PyTorch, and that's what the Officer Corps are the most comfortable with. TensorFlow is just as good. Just for sake of consistency, we'll stick with PyTorch. So all right. So one really nice thing about PyTorch is this TensorFlow data, tensor data type. And a tensor, as you can see over here, is just a way it's kind of like a list. It's pretty much like a list or an array. You can see down here, I've defined it's two arbitrary tensors, one called A, one called B, and tensor A, defined as like 1, 2, 3, just looks like a 1D list, right? And tensor B, so you can see it's like a nested list. So I got one list here, a second list here. It's a 2x2 array, right? And so this is just the output if I were to print the two tensors. Again, you can clearly see that this is a 1D list, like, or a one-dimensional array. And then tensor B is like 2x2, right? Are tensors clear to everyone? Okay. It'll be a lot more obvious. So you might be asking, okay, why don't we just use lists and arrays? Like, why do we need a special tensor data type? This will be clear a little bit later, but tensors also store really, really useful information like behind the scenes, right? So when you're doing your forward pass and your backward pass, your tensors are storing like extra information. We'll go over that in a little bit. Okay. So again, hopefully something like this is familiar to you guys. This is just like a neural network, right? So we have two layers, right? So that means, in both of these layers, we have neurons. So we have some indefinite number of neurons here. Let's say 10 neurons, right? And then our output layer, which are also neurons, we have 3 output layers. And each output, you might remember, produces a confidence value or a logits for each corresponding class. So remember, we have 3 classes, right? So this output neuron over here is going to say, hey, I'm class 1 gets a score of like 10. Class 2 might get a score of 5. And then class 3 might get a score of like -10, right? And so for classification, we just pick the output with the highest number. So in this case, if class 1 has like 10 and that's bigger than everything else, then our output is 10. Is that clear for everyone? Again, hopefully this should be reviewed. If not, let me know. I'm happy to answer any questions. Okay. So here is an excerpt from PyTorch code, right? This describes how we actually make our model class. So if you're familiar with object-oriented programming, this would be a class. If you're not, stay with me after lecture. Happy to go over it. So this first chunk defines defines each individual layer. And the second chunk defines a forward pass. So how does data, so we have these layers from up here. How does data flow through each layer? Okay, so starting up here, an end-up module is the parent class for all neural networks, right? And this is just kind of standard, right? If you ever make a neural network class, you need this end-up module, and you need call like super to call the initializer for the parent class. Again, these in Java, like this is just the inheritance in Python. If you've covered in Java, it should look very similar. Okay, so this is the interesting part. FC is kind of the convention for fully connected. You don't have to call it that, but that's just the convention. So a fully connected layer is a linear layer where each input is connected to every output neuron the next layer. So if you look at this formula down here, this is what's going on. So we're just multiplying a set of weights by the inputs plus the bias. You might notice we're missing the activation function. So a linear layer does not include the activation function. It includes the weights and the biases. So the first argument is just the number of inputs that layer has for a given neuron. So in this case, I have 4 inputs, right? 4 features, 4 inputs, right? And 10 is the number of outputs I'll have. It's also the number of neurons in that layer. So input, output. Okay. And again, hopefully that should be somewhat straightforward. And again, so as you can see for this first layer, right? I denote that I have 4 inputs, so 4 features, and then a total of 10 neurons, right? It's a little cut off here, so I didn't have enough space. Same thing for the next layer, right? Again, this is our output layer. So I'll have 3 outputs, 1 for each class. Okay. So forward, again, specifies how data should pass through that. So self.fc1, so X is our input. So a single line, a single flower's data, right? A single line in that table that we had earlier. So we pass that single data point through the first fully connected layer. We would then get 10 outputs. And remember, the activation function is not included in the linear layers, right? So we have to explicitly call the ReLU function, right? Torch.nn.functional it's like a library of all the different activation functions. So ReLU, we're just importing ReLU from here. Yeah. And so we then take our outputs from the ReLU layer. And again, by this time we have 10 outputs, right? We send those 10 outputs to each of the 3 neurons in the output layer, right? And so the output layer then, well, we have 3 neurons, so we have 3 outputs. Okay, so I went through that maybe a little fast. Does anyone have any questions about syntax or how information flows through? All right, perfect. Okay, so up here, the first line is we just define our neural network, right? We just define this class. Sorry, make an instance of that class. We make a new model object. Okay, perfectly fine. The next line is where we define our loss function. Remember, loss function tells us how bad we did, right? Last time we covered MSE, mean squared error, and MAE, mean absolute error. But both of those are for regression problems. Cross entropy is a loss function that's really, really kind of the go-to for classification problems. It's not as simple and straightforward as the other one, so I'll go through a quick pass of it. So over here, we have like the raw outputs, right? So, the model outputted the number 2 for the Setosa class, 1 for Varus color, 0.1 for Virginica. So this layer is like our raw output, also known as our logits. We then take a softmax of those logits. And what a softmax does is it represents our numbers as a probability, right? So notice that all of these numbers add up to 1, right? So again, it's just a really nice way for us to just conceptualize what these logits mean, right? So in other words, for example, we have the model thinks that the current input is of class Setosa with 66%, right? Okay, and so on this side we have the true probabilities. In other words, what is the actual like class, right? So in this case, the actual output should be Setosa. So the first neuron was right. And remember, our probabilities add up to 1. So if this one is 1, then the rest should be 0. And then we multiply everything by their corresponding probabilities, and we get an output of 0.66. So in other words, like what this slide is describing is we just take the probability of the correct class. So in that case, Setosa 0.66. Okay. I just cut off the neural network side from the left-hand side. We then take the negative log of each thing. Sorry, I missed the negative log step previously. So each softmax goes through the negative log. And then, so instead of 0.66 at the end, we have 0.42. And then we just sum that up. So our final loss is 0.42. And so that's what this equation over here, very ugly looking equation describing. So just for terminology, y hat I, like y hat always denotes a prediction, right? So these softmax probabilities. Yi denotes like the true value, like the true probability. So in this case, 1, right? Okay, so that's cross entropy loss. Any questions about how that's calculated or why we use it?
Why is there a negative?
Great question. Remember, we want loss to generally be positive, right? If we take the log of a number between 0 and 1, it'll be negative. So log of 0.66 would be minus 0.42. So we take the negative to like invert that. Okay, and remember our inputs to the log function, because we do a softmax before that, right? That means every single output will be between 0 and 1. So in other words, this input x will never be negative and will never be a number greater than 1. Is that clear?
Yeah.
Perfect. Okay, so just a recap of the loss functions we've gone over. We have mean squared error, so the true value minus the predicted value squared. Mean absolute error, same thing, but absolute values instead. And these two are for regression. And we just went over cross entropy loss here. Binary cross entropy loss is pretty much the same thing. It's just you just have 2 classes. So I know this looks slightly more complicated, but it's literally the same thing, slightly faster, but it just considers two classes. So binary classification, if you're from first lecture, it outputs yes or no, 0 or 1. Okay, so we're now down to this last line, the optimizer. So the optimizer calculates like the weight updates, or sorry, decides how we should update our weights. So before we updated our weights from last lecture by gradient descent, and remember that's where we took the derivative of each parameter with respect to the loss, and then we updated our weights in that direction, our weights and biases in the direction of the gradient. Atom isn't like all optimizers use that principle of gradient descent. We're still, calculating gradients, moving in that direction. The difference is Atom is a lot smarter. So you might remember from previous lecture, if we had like a local minimum, like we could get stuck there. So in other words, anywhere where there's a dip, like gradient descent just gets stuck. Atom is slightly smarter, doesn't get stuck there. It can, but it's a lot more robust. Atom is a lot faster as well. So in other words, gradient descent, but better is Atom. Like I would not recommend using naive gradient descent. But yeah, is why we use an optimizer clear? Okay. Again, we'll cover how Atom and other optimizers work, maybe in a future lecture. There's interest. Okay. So this is some code that goes over like how we actually train our model, right? So I know it looks like a lot, but this is all things we've seen before. So if you look at this inner for loop, we're getting our inputs and our labels. Remember, our labels are like the true values. We then run the inputs through our model to get the outputs. We calculate the loss using the criterion. Again, criterion is just our loss function. Optimizer.zeroGrad, just I'll cover that in a little bit. But the really nice thing is that we do all of backpropagation in this single line, loss at backward. That calculates all of our gradients. And then the optimizer in optimizer.step updates the weights using those gradients. So in other words, all of backprop is done in like these 2 steps, which is really nice. In practice, you'll pretty much never have to really do like backprop by hand or code it manually. Okay. And here we're just, logging our loss at every time step. But yeah, okay. But let's go back to like the top of this for loop because we have some unfamiliar terms up here. For our epoch and number of epochs. So an epoch is like an entire forward and back propagation over the entire data set. So if we have like k epochs, we do like the model like passes through the entire data set k times, right? So one epoch is one time we go through the entire data set. Okay. Hopefully that should be clear. Okay. Model.train just sets up the model in training mode. Model.eval sets it up in testing mode. To be honest, for like this current notebook, I'll share it after lecture. They don't really do anything. They do have a tangible difference once we have way more complicated things inside of a neural network. The reason I have them here anyway is just for good practice, right? Again, functionally right now, they don't do anything. Once we have more advanced things like dropout or normalization layers, we'll revisit that. Okay, so moving on to the inner for loop. So you might notice that we have for batch in train loader. So a batch is just a small subset of our data. So if our data has 410 like data samples, in this case we have 150. But if it did have 410, we can split that like entire data set into like these mini data sets of like 64, right? These batches. So you might ask, okay, why do we like handle our data in batches instead of one by one? Question. No. You can set them to whatever you want. In this case, I've just set them to a batch size of 64. Okay, good question though. But yeah, you might ask why bother like. So the model sees an entire batch versus a single input. So in other words, we're doing 64 inputs at once versus a single input. So why do that? Before we get there, let's talk a little bit about like how does grouping up our data and sending that through the model like change the process? The nice thing is it barely changes our process up. I have it here formally just in case you want to see it, but what it really changes is how we calculate our loss. So this is just a quick key. It's in case you guys want to review the lecture later. But essentially, we have so if this is a loss for a single point I, for a single like row of data, all we do for like our batch loss is we just take the average of that, and that's it. So if you have n, like if our batch is 64, like if n equals 64, we just sum up all of those individual losses and divide them by 64. So the batch loss is the average loss across the entire batch. Pretty straightforward. Our gradient is very similar. It's also just the average gradient, like across all the other gradients, right? And so, the way we update the parameters is the exact same. By the way, theta is just, the variable standardly used to represent your parameters, like your weights and biases. So the way we update our parameters is still the exact same. So parameter minus the learning rate times the gradient. So in other words, the big thing you guys need to remember is the batch loss. Like when we do batches, we just take the average, the loss, and the gradient. Okay, so here I've compared the individual, like training on individual data points versus like the batch loss and the pros and cons. The big thing is that because the model's handling like 64 data points or 128 data points, like this batch size of inputs at once, you're storing more things in memory, right? So if you have limited memory, well, then you might need a smaller batch size. But the pro of having a bigger batch is that one is faster, right? Having a bigger batch does like make your model somewhat faster, but it's not like one-to-one, right? So like, a batch size of like 5,000 might be somewhat faster than batch size of 4,000, but like in those early steps from like 1 to 4 to 4 to 64, it becomes a lot faster. The other thing is that it's a lot less prone to noise. So before, if we update our model each time for like one data point, right? Well, what happens if you have an outlier? Then the model makes a big step for a data point it really should be making a big step for. By taking the average, well, now we're kind of silencing those noisy data points. So just to recap, if you have limited memory, maybe go for a smaller batch size. But the pro of having a bigger batch size is that you can, it's less noisy, like because you're taking that average, and it's faster. We'll cover, actually, yeah, that's pretty much it. Okay, so let's actually see the code now. And I've been hiding it from you guys for now. Okay, so here is where I made the data loader. And so again, the data loader is just how we process, it's kind of like a container for our data set, right? So you can see here that, hey, for the Irish data set, I have 120 samples and the test size is 30, right? Okay, so I have an example of just basic math with tensors. So for example, if I add two tensors, in this case, A by itself, it might be a little hard to see, but it just does like element-wise addition. So in other words, if I add this tensor, 1, 2, 3, plus that tensor again, 1, 2, 3 plus 1, 2, 3, it would give you 2, 4, 6. Straightforward element-wise addition. Subtraction is the exact same way. Multiplication has a little bit of nuance to it though. So if you just do A times A, or like, tensor times tensor, right? It will do element-wise multiplication. So what that means is, again, if I do, what is it? A times 2, right? It will do, well, 2 times the first number, 2 times the second number, so on and so forth. If I did A times A, well, it would do 1 times 1, and then 2 times 2, and then 3 times 3. So every element is being multiplied by the corresponding element of the other thing, right? But matrix multiplication, though, is a completely separate operation, right? So if you remember, that's row times column for the two matrices. If you're not familiar with matrix multiplication, I highly recommend reviewing it or staying after a lecture. I have a few slides for that. But again, I just want to make the distinction that we treat element-wise multiplication and matrix multiplication as two different things, right? So just be aware of that. Another nice thing is that we can reshape our tensors, right? So before, this A tensor was just, what is it? 1, 2, 3, right? So it's like 1 by 3, just one row. Now, by reshaping it, we have a single column, right? So you notice it's been reshaped to 3 by 1. Okay, just a few useful operations. I highly recommend, maybe after lecture, just checking these out. Okay, but here's the interesting stuff. So I've already covered how to create the class. I've covered what these guys are. Okay, now to the training. So yeah, Number of epochs, again, that's the number of times we iterate through the entire data set. So I've set that to 75, which is a reasonable number for now. The batch index is just the batch number I'm on. So for example, batch number 0, batch number 1, so on and so forth. A single batch contains the inputs and their corresponding labels. So in this case, I would have, since I've set a batch size of 64 all the way up at the train loader, I would have 64 inputs, 64 corresponding labels. Okay, let's go ahead and just, I've already run this from beforehand. So if there's anything you learn from this notebook, it would be this: pay attention to your shapes, right? Pay attention to your tensor sizes. And that should be like the key takeaway from this notebook, right? You'll notice that, oh, sorry, I said a batch size of 16, not 64. Sorry for the confusion. You'll notice that I have the input shape. So this is the thing being input to the model is given by the batch size and the number of features, right? So in other words, I have 16 inputs here. The label shape is, well, the correct label for each input. So again, if I have 16 inputs, I should have 16 labels. If I had 17 labels, then something's gone wrong. So the model, remember, we have 3 classes, right? So we have 3 outputs. So if I input a 16x4 matrix, or sorry, a 60x4 tensor, I should have, well, 16 corresponding outputs, but I have a score. I have 3 numbers per. So for example, this might be a example output for like a given input. So this first element is the logit, or like the raw score, not the probability yet, just the raw score for the first class. And this would be the score for the second class. So just looking at these numbers, so -2, -0.9, 2, 0.2, which do you think the model would predict as like, oh, it's this class? Class 1, class 2, or class 3? Class 3, right? Because it's the biggest number. Ooh, if you guys said class 0, I'd be freaking out right now. Okay, perfect. And so we have 16 outputs, and we also have 16 labels. So the label number corresponds to like what the actual correct class is. So sorry, it's 0 indexing. So I should have said class 0, class 1, class 2. So for this label, for example, for this label, the corresponding, sorry, for this output, the corresponding correct label would be like the second class, or like class index 1. In other words, the model is wrong for that label, right? Okay, which is to be expected, right? Because this is the very first epoch of training. The model is like all randomly initialized weights. Okay. So, yeah. So this entire thing denotes the training loop. Down here, I just want to focus on, I separately have a testing loop, right? So what's going on here? We start with torch.nograd. And so the really nice thing about tensors is that when we do that forward pass and the backwards pass, it's keeping track of the gradients, like implicitly. We don't have to do anything, right? It's keeping track of the gradients, keeping track of those intermediate values. However, down here in our is where we denote our test set by the test loader. We don't care about those gradients. We just want the model to output a number so we know how good it is. So in this case, we disable the gradient calculation with torch.nograd. So everything inside of like this section, like the model is not keeping track of gradients. So again, this is a very important distinction to make. By default, we keep track of the gradients. In this case, we're explicitly telling the model not to do that. Okay, otherwise, the process is the exact same, right? Yeah, okay. So I won't go too much into the matplotlib graphing code. I encourage you guys to look over it later, but you can see that the training loss and the test loss are both decreasing. Does anyone think we're overfitting or underfitting if both losses are decreasing equally? Not exactly. Well, we might. We would underfit if the training loss was like if both the training and testing loss were really high, right? So to be fair, we might be underfitting, right? Like we're at a loss of like maybe 0.5. That might not be too good. So yeah, we might be underfitting actually. So if I were to run this a second time, hopefully our loss would be slightly lower. Oh, let's take a look. Yeah, so earlier we stopped at 0.5. Now we're a lot lower to like 0.3. So actually, yeah, you guys are right. We probably were underfitting at the time. But again, I want to make the distinction that the test and train loss are both roughly similar. So we're not overfitting. If the test loss was a lot higher, then we would be overfitting. Okay. Here I just have some code to calculate the accuracy. Let's see how well we did. Oh, 100% accuracy. That's pretty good. So again, this is why we have the difference between accuracy and loss, right? Because like, 0.3 seems good, but like 0.1 sounds a lot better, right? It's like we don't have an exact metric about how good our model is doing based off loss. Accuracy straight up tells me, hey, you got 100% of the samples right. Like you're good, right? You probably don't need to train any longer. Okay. So I encourage you guys to look on this separately. I won't go too much into it. Another important thing in this case, so we've trained this nice model. We're very happy with it. We can now save it with torch.save, and we can later load it with torch.loadStateDictionary. Okay, so again, this notebook, the link to this notebook is on the slides, which are on the website. I'll also post the link in the Discord. Question? Yes. Great question. Great question. So, okay. So right now, so by the way, these are you might have noticed that I trained our model for a second time. So you might notice that these outputs are looking a lot better, right? So in other words, which output does the model think is correct for this line?
0.
0. And the corresponding label is 0, right? So if you check every single line, you'll notice that the model got all of them correct. But why is the loss still 0? And it's because this is the way cross entropy is calculated, right? Again, if you took the softmax of these numbers, in other words, if you were to represent these numbers as probabilities, right? You would get maybe this is like 0.98. This is like 0.0. Actually, it'd be more extreme than that. This would be like 0.9999, right? But it wouldn't be 1. And that's why, right? So if somehow this was negative infinity and that was negative infinity, then in this case, cross entropy loss would tell us the loss would be 0, right? But in the case where it's like 0.99%, well, the loss would still be above 0. Does that make sense? Okay, perfect. But again, that's good. Like we like that. 0.99% confidence is like really, really good. Okay. Any other questions about the code, or maybe I skipped over something and you want me to go over it again? Okay. Otherwise, that's it. Again, I highly recommend going over the parts I kind of skimmed by. Otherwise, Vinny will introduce the math wizard, but before he does that, I just want to show you guys what that builds up to. So we have this nice leaderboard, right? So Vainateya and Vias worked very hard on creating our first in-house competition. So we've kind of presented a problem for you. Vinny will go over it more. But as you guys submit things, it'll be on the leaderboard. So you'll notice that our very own Vias jacked up his score. None of you will reach that. But yeah, as you guys submit, it'll populate here. It'll be nice to just, have a friendly little competition. But Vinny can talk a lot more about the logistics of that.
All right, guys. So this is like a really fun competition / training exercise, just to get you guys familiar with how to build your first neural network using PyTorch. And so, okay, we're calling this Math Wizard. The main idea is that we basically made this template in Google Colab that you guys can use to create just a basic neural network class using PyTorch. So there's 2 parts to this assignment, right? So the first is you guys can define any algebraic function as a function of x that you guys have. So like x squared, x cubed, x plus 5, you get the point. And then once you define this function, then the idea, you guys, look, by the way, the link at the bottom, make a copy of the textbook or make a copy of the notebook so you guys have your own personal thing to work with. But once you basically define any of the algebraic function that you guys want, you're going to fill out the code for the model definition, the training loop, and stuff like that. And then you're going to train it to see how it does on the function that you guys created, right? So pretty straightforward. But the second part is the competition part. And so for this one, we're going to give you 3 data sets for 3 mysterious functions. So these are functions that we know, but you guys don't know, right? And so you're supposed to optimize the parameters of 3 separate models. You have to basically make 3 trained models for each of the function data sets that we create, and then optimize, the learning rate, the parameters, the size of the model, and all that stuff to basically get it to be as accurate as possible. And then you're going to send those 3 trained models to us. We're going to run it on our data sets that we have on our end. We're going to update the leadership or the leaderboard with your aggregate score on how well you guys do on all 3 of those data sets. Okay, so I'm going to quickly jump through like the link to the textbook just to familiarize us with the different parts of it right now. But before that, does anyone have any basic questions about the general idea though? Yeah. Right. Thank you. So basically, you can spend the rest of today just to, work with a template, create the basic neural network. As long as you guys understand how to create the model and then submit it to us, that's all like the main, goal is for today. You'll have an entire week starting from today to the end of next class to fine tune your models, figure out the parameters, get it all set up, and then submit to us by next class. And then next class when the leadership updates, we'll kind of, I guess, figure out who the math wizard is, right? Who is the one who created the best model that converged the best on our data sets. All right. Okay, yeah, but okay, cool. So I guess, yeah, feel free to this should only be, I don't think, yeah. Yeah, okay, this should not be edit only. I hope you guys aren't able to edit this. But yeah, please make a copy of this though. Right. So the first part, this is really I tried my best to organize this in a way that makes the most amount of sense. But the main idea is after you guys import packages, this step 2, the whole data loading pre-processing stuff, you guys, it's not really that important towards the actual setup of the model. This stuff is just defining a data set that creates based on the function that you guys create, this will create dummy data for that function. So if you guys decide sin of x is the function, this basically creates a data set that you guys can use. And this is just a function that when you plug in a data set creates train loaders and test loaders that you guys can use to plug into the model, right? So right here is where you guys are able to define your own custom function. So in this case, right now, the function is just y equals x squared, right? So it takes in some x and then does something to it and then returns that y value for it. So this is where you guys can just plug and play with this and define any function you guys want. So this section right here, this is strictly after you guys have done implementing the training loop and the model setup, and you guys ready to do the competition. When you guys ready to do the competition, we'll come back to this later, but you're just going to uncomment these 2 lines and run them to work with this, right? Yeah, so the rest of this stuff is kind of just playing around with the test loader train loaders. You have to understand that step 3 and step 4 are where you guys are going to be writing the code for this stuff, right? So for step 3, we're going to be essentially building out and fleshing out the model. So using nn.module to do so. This is the model class. And then we have the forward method as defined over here as well. So you guys are going to be fleshing out this stuff. And then you're going to decide, what the input size is, the hidden size, the output size. And then, what the loss criterion is, the optimizer, the number of epochs. And then you're going to write your own train loop down here. And then when that's done, you're basically going to run this and then, train your model. And then finally, you'll be able to save the model. But this is just the first part of the assignment, just plugging and playing, understanding how to work with the functions. The part that's the actual competition will come from the part that I mentioned earlier, right? So essentially there's 5 steps you have to do for the competition. So we're going to provide you guys with a zip file. This zip file will contain 3 data sets. So you're gonna run this line to unzip the data and basically store it in the content folder. So on the folder on here on the left, in the folder here on the left, you'll have the content folder. So you're basically gonna make sure the zip file is somewhere here. Once you download it and then you drag and drop into the content folder. Once that's there, you'll run this line to unzip it and have 3 separate data sets. You're gonna run this line to choose one of the 3 data sets, and then you're basically going to update this custom data set here to custom competition data set once you run that line right there. And then that's it, you're basically done. So after changing those 3 things, you can run, with the code that you have, make additional modifications to the code you've already written. And then this will allow you to basically create a model that is fit to one of the three data sets. And then once you make your own decisions and you're happy with it, save it, save it on your local file and do the same thing for other two the data sets as well. And then once you have all three of the models saved, just upload them as a zip file to this following drive link, and then we'll update the leader board. Yeah.
For submission, what sizes should they use for the input and the output?
Right. So you mean for like the zip file that we submit?
Because they're gonna submit the model, right?
Yeah.
And they get to decide, for example, what the input size, what the output size, and what the input size is, right?
Yeah.
But for submission, what should the input and output size be?
All right. Wait. I'll put this in Discord. Well, I have like the input and output sizes that we use when we're training it. We'll just have them do that one.
Which should be one.
Yeah.
Yeah. So, so when you're submitting, so, you know, you're free to play around with the model, and have different sizes for the input and the output, which basically means, for example, you have functions which are which have higher dimensionality, but for the submission and for actually, you know, for this leaderboard, please use one for the input and the output size, since we're using a function in one dimension.
Yeah, I'll make sure I add the note in there as well. Yeah. Is there anything else you guys want to add? Or... Okay, cool. So with that being said, we're gonna give you guys a little bit of time until the end to kind of work with this. I'll be going around and helping people out. But yeah, let me know if you guys have any other questions though. Can we on the lights a little bit?
Yeah. Once again, thank you, Vinny and Vios, for spending the last 3 weeks on this. Yay.
Sorry.
All right. And that marks the end of today's lecture.
Yeah.